Okay, thank you very much. Looking forward to this meeting. Looks very stimulating. I'm going to talk about patterns in particular types of systems that are rotating fluids or stratified fluids, mostly stratified fluids today. Probably many of you have heard me talk about rotating fluids in the past. Here we have a fluid that is contained between two cylinders. Inner cylinder is rotating. The fluid is visualized by putting some small flakes in it, and you can see that there is a pattern of waves that are traveling around the cylinder. If you increase the speed of the cylinder, then you reach an instability in which a second wave comes in, and you have two characteristic frequencies. But if you continue to increase the speed further, at some point you reach an onset of a different type of behavior which is erratic in time, and if you characterize it, it is a form of chaos. That is, you can characterize it in phase space, nearby points in phase space separate exponentially fast in time. So that's just one example. Here's another work of Tom Solomon. Tom is here, maybe. Yes. At the University of Texas on another rotating fluid. So this is a rotating tank about 1 meter in diameter, and you have a flow that is produced by pumping fluid into the tank, and what you get is a series of vortices that form spontaneously at some speed. And if you look at the motion of individual particles that are in this fluid, passive scalar particles that just follow the flow, they'll move around in a vortex for a while, and then they can escape a vortex and make a trip to the next vortex and stay, and then after a few rotations, maybe make several large rotations, make a long levee flight. This is a type of diffusion of the particles in the system where you have these short and long trajectories interspersed, and it was a kind of anomalous diffusion which was discussed theoretically but not observed in any experiments until this work of Tom Solomon and Eric Weeks. Another type of flow I'll be discussing today is one that occurs when water in the ocean, which has waves internal to the ocean that come up the continental shelf, and they pick up material from the surface, possibly, and carry it up the shore. And how much material is picked up and how this happens is the subject of current research. That's a recent picture, and work is not yet published. So let's go now to Jay Feinberg. We're here because we want to celebrate the exploits of Jay Feinberg. In 1988, you see here, 1988, he sent an email. There was no internet. This is prior to the internet, World Wide Web, but there was BitNet. And he sent this email. Says, I'm a graduate student at Weitzman. Now, I'd never heard of this guy. But I read on further, and I saw, Professor Victor Steinberg. I had great regard for Victor Steinberg. I met him in the 1980s, early 1980s at the Weitzman, Santa Barbara, University of California, Santa Barbara. He was working with Gunther Ahlers, and I'd followed his work. And so I was inclined to read further and check this out. And I, wrote back, Dear Mr. Feinberg, thanks for your letter and so forth. I said, maybe we should talk further. And I used, likewise, we were at the cutting edge of technology of the day. So that led to Jay's coming to Texas in 1988 in the fall. And Another person who came at the very same time was Dan Lathrop somewhere there. There's Dan. Dan just graduated from Berkeley, and he came as a PhD student to UT. And the three of us talked about some possible projects, and one was to study turbulence in the system of rotating cylinders, and to really look at ultimate turbulence, to make the system as turbulent as possible. That means you spin the system, the inner cylinder, very fast and characterize the flow that occurs. So Dan and Jay are very good designers, engineers, and they put a lot of thought into the design of the system. You want to spin the system very fast, and you want to reach high Reynolds number, make it fairly large. This was much bigger than the little systems we've been looking at. It's 0.7 of a meter high, and you want to spin the cylinder fast to get to high Reynolds numbers. Here's a 2 kilowatt motor, and I think really it was Dan that was thinking about, well, that 2 kilowatts of power goes somewhere. It goes into the fluid. It's joule heating of the fluid. And then the fluid's going to all heat up and boil, right? So we've got to cool it at the same time. So we need a refrigerator that will cool with a lot of refrigerating power, several kilowatts. So there's coolant here with copper rings around the top and bottom, and the heat flows in the fluid. The fluid at that high Reynolds number conducts well, and you conduct the heat out. And you rotate fast. Well, how fast can you rotate? We wanted to go as high as we could in Reynolds number. But how does the dissipation depend on the Reynolds number? And that became the question addressed in the experiment. How fast does the torque increase with the Reynolds number? And so they measured torque, being concerned about the effects of the ends, boundary layers formed here at the ends called Ekman layers, separated the system into 3 cylinders, and measure the torque in these cylinders. These rigidly rotate, the upper and bottom, but the torque arm connected to the center cylinder. A lot of engineering went into it, and we checked with a professional engineer, make sure the design was appropriate, and we got, even as we turned it up, we saw the fluid becoming turbulent. So most of the experiments have been done at that point at a Reynolds number of a few thousand. We got up to a Reynolds number of 6,000, and you can see that the nice smooth vortices that we had before are gone. We have something that's very irregular. But this is not terribly high Reynolds number. How high can we go? This is an image that's made by putting small visualization particles, passive scalar particles, in the flow that enable you to see the pattern. So turning up the speed, you can measure the torque now. This is torque on a log scale versus Reynolds number, starting in 1,000, 10,000, 100,000, going up to 1,000,000, or even higher than 1,000,000. And what you see is that these guys are great experimenters in that look at those data. You don't see much scatter. Very precise, very repeatable data going up. And they're so precise you can take the derivative and see what the exponent is. And that's what's plotted here. And we thought that the exponent would have some value that would be constant over some range. You'd have some range in which you have a characteristic exponent describing the torque of the system. But what was found was the exponent continued to increase, albeit slowly, but it was getting up towards 2. And we wonder, how high can it go? And why didn't we go higher than 1,000,000 Reynolds number? That was all the heat that we could remove with our refrigerator, right? So that was the limit, but that's pretty high. And in fact, if you think about the amount of power dissipation, this exponent for the torque is nearly 2. Torque times omega is power. So the power is going as the rotation speed cubed, approximately. So we hope maybe to go to 10 million, not million, but that would require not 1 kilowatt, but 1 megawatt. 1 megawatt motor and a megawatt refrigerator. So that becomes a national lab experiment. So that's, and in fact, as far as I know, to this day, no one has gone much beyond this in Reynolds number. Deadlift Losif?
No, Matt Paletti went to 5 million.
5 million. Okay, but not 10. Yeah, Deadlift Losif has in 20, Netherlands, has a big system and it's gone up to several million. Matt Paletti has gone to 5, but you don't go up by factors of 10 because of the power dissipation. So we wondered how can the Reynolds number, this scaling exponent go? And there was a person, Charles During, who had been at Texas. He was a PhD student at Texas, and he was my teaching assistant when I was teaching statistical mechanics. But he was now he's a professor of mathematics at University of Michigan. He and Peter Constantin worked directly from the Navier-Stokes equation, which is unusual to actually prove something from the Navier-Stokes, and found there's an upper limit that this exponent has an upper bound of 2. And what happens between 1.87 here and 2 is unknown, or not yet established. So that was a very nice experiment that without Jay and Dan would have never been done.
That was Dan.
With it. Okay.
You guys kept me safe.
Now, fortuitously, at the same month, September 1988, a new assistant professor arrived in our department, Professor Michael Martyr here, who had worked in statistical mechanics with Jim Langer at Santa Barbara and then with Leo Kadnoff at Chicago. He came to Texas and he told me when he interviewed that he wanted to study fracture. He was interested in fracture. He'd never done anything in fracture. He didn't know much about fracture, what had been done, and what approaches he would be able to take. But he set upon himself upon studying fracture. But he said from the very beginning, he had done theory. He'd never done experiments, in kitchen experiments, but not in the laboratory. And he recruited, let's see, he recruited Jay Feinberg, who knew nothing about fracture either, as far as I know. I mean, except personal experience of dropping a beer bottle, but to develop laboratory experiments. Now, we didn't have any grant, no funding, so they had to work in designing equipment and in building it from scratch without funding. And that's what they did and got some very nice results. And here, one weekend, it's never happened again, but one weekend our whole lab went together on a camping trip to Pedernales Park. And here's Michael here. Now Jay, if you look at all the people in this room, this is more than 25 years ago. Most of us, that's me, most of us look different. Jay looks the same. Michael looks a bit different, but well, he certainly has less hair, but anyway. So Mike charged Jay with building this experiment, which they did from scratch, made in a machine shop, designed it very carefully, lots of discussions about the engineering. And Jay worked with a new graduate student who was just starting research, Steve Gross. He's now a professor at UC Irvine. And they built this system, and they became very serious scientists, as evident here with the white coats. You see. And Professor Barter here will talk about that work, I guess, at some point later in this meeting. Now, you know, I learned so much from working with Jay and from Yvonne and Michael and Dan and Tom Solomon, Lorette Tuckerman, and others who were at Texas at that time. I just wondered, though, Jay's been away 25 years plus, and wondered if he had any memory of his actually being in Texas. But apparently there is still some recollection of Texas as it was called.
Well, look at this curling leaf.
Yeah, there's a lot of wavelengths in there, a lot of curvature, and they're also pretty green.
That started in Texas, didn't it? Didn't you start that with Harry?
Yeah. Many things started in Texas.
Yeah, that all looks kind of like Taylor Quit to me, but you know, I'm not a real botanist here. But you know, obviously the way that we think scientifically, our scientific thinking has been heavily influenced by both Texas and Harry.
Yeah.
But our personal lives, you know, I don't think so, not really.
No.
Oh, wait a second. Oh, Mrs. is calling. I gotta go, guys.
Okay, hand me a long neck there, boys.
I'll go fix some fences.
Okay, yeehaw! Yeehaw! Woo! Okay, hold on, Chunky. Yeehaw, boys!
And Jay learned horsemanship, as you can tell. Okay, so I thought I'd go and talk about some more recent work, and in particular a topic that has occupied a good bit of our time for the past 10 years. And that is the generation of internal gravity waves in the oceans. So what we have here is some synthetic topography meant to look like the ocean bottom, and we have tidal flow flowing back and forth. So the tide flows over the topography and produces the waves whose intensity is indicated here in red that travel up. These are called internal waves because they're internal to the ocean.
What was the typical scale of the roughness here?
In
The real ocean.
In the real ocean, it could be 100 kilometers. I mean, we can look at it on different scales, and of course, you have topography on finer and finer scales, and that's a good question. How do things scale? And we're concerned about that. Okay, first, just background. The ocean is stratified because as you go down in the ocean, it becomes colder, and it becomes saltier. So the density increases, not talking about the increase in density due to the compressibility of water, which is not very compressible, but the density increased due to the salt and increasing salt concentration and lower temperature. And if you imagine a parcel of fluid that is neutrally buoyant, has the same density as the fluid around it, and now you perturb it upward, so it's in a region where the density is less, then it's going to sink. And it will oscillate, and it will have a natural frequency of oscillation, just like mass on a spring's frequency is equal to the square root of k over m. Here your spring constant is really given by the density gradient in the vertical direction. So that gives you a restoring force. And that disturbance then will disturb the fluid near it, and the disturbance propagates. And those are waves internal to the ocean. They're density perturbations that propagate in the ocean. Now, these are peculiar waves. Now, that's interesting. Well, I'll skip that. The waves will move particles oscillating back and forth in this direction, as the arrows, which are velocity vectors, are indicating, and the phase is going to propagate perpendicular to that. So you have phase velocity and a group velocity in perpendicular directions, which is an unusual type of wave propagation. If you look at a particle, passive particle sitting here, it will just oscillate back and forth. There's no mass transport of particles in this situation in the open ocean. Okay, so this is of the open ocean by Carl Garrett at MIT, and it has very different scale vertically and horizontally. So ocean depth is typically 5 kilometers, and this scale might be 10,000 kilometers. So it's a big difference in the vertical and horizontal scales. And when the tide goes over a mountain or a ridge here, then it produces waves which travel at a certain angle. This dispersion relation gives you this angle up here. Angle is the frequency of the tide divided by the buoyancy frequency, natural frequency due to the density gradient. And it will travel from the point of production of the waves and that with that angle in the 4 directions. So this is called the St. Andrew's cross. And similarly, waves are produced by in the bottom, and here you have waves flowing over the continental shelf break. So these waves account for more than half of the kinetic energy in the ocean, and that energy also drives currents that affect the climate. And it's important to understand how much power is in the ocean arising from this conversion of the gravitational energy of interaction of the Earth and the Moon and Sun, that is the tides, into this wave energy. Waves are generated locally but can propagate 10,000 kilometers. Does this make a difference? Well, if you look at the whole globe, at the globally average temperature and the deviation from that average at any particular latitude, the deviation is small. Here's a little bit colder than average, and in the Himalayas it's actually much colder than the average. But one place stands out on the Earth's globe as being different, and that's Northern Europe. Here you have Britain and Scandinavia, and you see it's 5 degrees Celsius hotter than the zonal average at that latitude, and even 10 degrees in some regions. And where does that heat come from? Well, it comes down from the equatorial regions and from the Gulf of Mexico, and it's carried up by the Gulf Stream, which is slowing down for reasons we don't understand. No one understands. Okay, which maybe for the long term is not good for some people. So it's interesting to study this issue. Now, do these waves have any effect on the topography of the ocean? You look at the standard ocean bottom as you come in from the deep ocean. Half of the ocean is 4 kilometers or deeper, half of the ocean is less. So 4 kilometers is a middle number for the depth. And then you go up a continental slope, and then there's a shelf break, and then you have a continental shelf, which is almost flat. But the question is, what determines this continental slope angle? Well, if you pile dirt, you get an angle of repose of maybe 30 degrees or so. But if you look at the angle of the continental slope, as was done over the whole globe in a very nice survey by Caccioni in Science about a little over a decade ago, he found here is a continental shelf off New Jersey. There's New Jersey, this region we're looking at. And here you go from here to here. The depth is only increased 50 meters. And then you get to a point where you go a little further, you're 1,000 meters down, 2,000. So this is the continental slope right here. This is ocean bottom. And he looked in their research there at the angle at which the internal gravity waves propagate and the angle of the topography, and he found that right in the region of the continental slope, which is green here, that ratio is 1. So the waves seem to have the same slope as the topography. So we decided to look at that in some experiments to understand why that might be. Now we have a little over a meter long, and you have waves that are produced by oscillating. Here we oscillate the topography rather than water. It's easier. So the topography oscillates, and we have a gradient in density from the bottom to the top by making water saltier at the bottom than it is at the top. With a constant gradient in density, then we have a constant value for the buoyancy frequency. And now if you, something works. You can see the particles suspended in the flow in this laser light sheet are moving rapidly near the boundary and slowly further away. So you have a boundary current here. And you analyze that. Now, when the wave angle and the frequency is such that the wave angle here is different from the slope angle, you get the ratio of the maximum speed here to the tidal velocity is order 1.5 or so. So it's similar. But if you go to the case where the internal wave speed the internal wave is parallel to the boundary, the speed of the boundary layer is much higher. This is an order of magnitude higher than the tidal speed. So you have a very rapidly flowing boundary current which picks up sediment and over millennia or millions of years apparently shapes the angle of the continental slope. So if you look as a function of frequency, you can see that right at the point where you have the frequency of the waves give you an angle that's the same as the continental slope. You get this maximum. Very strong currents drive that. So that provides a potential explanation for the angle of the world's continental slopes. Now, this is something that we read and intrigued us, that if you have these internal waves that have been propagating 1,000 kilometers, 10,000 kilometers, they come up on the continental slope here. This is the actual dirt in the continental slope off of the Oregon coast. As they come up, they can trap the sediment or the fish or marine life and carry it upslope. So there was speculation that this might play a role in coastal ecology, in the biota being brought up shore, and also nutrients and oxygen depleted water. So here we have, this is present day in Austin, a 4-meter long tank with a density of the fluid fairly constant here and going through a transition, which is what happens in the ocean near the surface. There's a region where you have this warm, well-mixed, low-density fluid, and then you go down deeper and you get to colder and saltier water. So there's a transition as you go down, but the value of the density continues to increase as you go down. And then here we have a continental slope. So we have internal waves that have been generated some way down the tank, and they propagate in, and they hit the shore, and they form a bolus. That is, the current moves up and there's overturning, it traps fluid.
Harry, what's the definition of the word bolus?
It's a vortex that traps fluid.
And shoaling?
Shoaling just means moving up the shoals. Moving upshore. Just moving up. Yeah. Thank you. Okay. So this is the most recent data, not yet published, but I hope in another 2 or 3 months it will be. And here you have in the co-moving frame of this dye here from the experiment, you can see the water, it's moving upward, so these are velocity vectors for the water, and that's laboratory experiment. Here's the corresponding simulation. And we want to see how much matter is trapped here, so we use some techniques from dynamical systems, Lagrangian coherent structure analysis, to identify the particles that are trapped and carried upstream. Okay, now to the real question is we would hope to address is energy flux in the ocean. Well, energy flux is given by pressure times the velocity. So work is force times velocity, force times distance, right? Or power is force times velocity if you have some constant force. And so that usually is just like power, force times distance. And we want to integrate that over some surface S and calculate how much power is transmitted. That's the job. Well, that's been done theoretically, but theorists like to do what they can with linearized equations, but the Navier-Stokes equation is very nonlinear. But the linearized equations give you a result that the power is proportional to the speed squared of the tide or the flow times the buoyancy frequency times the height of the topography. And this is for flow over small topography. Tidal flow over small topography. Now, that means to calculate using this result of Llewellyn, Smith, and Young, you need to know what the tidal velocity is. You need to know the topography, how it varies with the location, and the local buoyancy frequency. So, first, let's look at the buoyancy frequency. The buoyancy frequency assumed here is constant. And almost all the analysis and most of the calculations of the energy in the ocean from these internal waves assumes that the buoyancy frequency is constant. So we looked at the data set that had been acquired in a huge experiment of 30 countries where they collected 30 different locations. They would drop a line and measure the temperature at that particular point, salinity and pressure, and all the way to the bottom, every 20 centimeters sometimes, or every meter, but from the surface down to 7 kilometers, whatever distance. So this body of data exists online, but apparently nobody ever analyzed it to look at the way this buoyancy frequency depends on Z. And here's results. This is mainly the work of Greg King and a group of others of us, but he was a high school student. He's now a PhD student finishing in Chicago, but at the time he was a high school student. And he calculated, and one of the many things we found interesting now looking as a function of depth at this buoyancy frequency is that data taken in different times, like 89 and 94, 5-year separation, you calculate this buoyancy frequency here, which is, this is not the raw data for density, this is a derivative. So you're taking derivative of data and look at the reproducibility. And these different colors are ships from different nations. Green maybe, say, is Italian, red is Spanish, whatever. And they agree remarkably well. And they don't change in time. so that the data is reproducible and it's time invariant. And that's what's generally found if you get below 500 meters or 1,000 meters, that the ocean changes, the ocean velocity distribution and the density distribution changes very slowly, time scale of a millennium, not years. This is just, so there are 18,000 data sets. This is taking 3 points, just here, here, and here. But you can look with these data all over the ocean. And the other thing to notice is N is not a constant. And these calculations of the power, assuming N is a constant, are going to be poor estimates. Now, how does it, if you take data over the whole ocean, as Matt Paletti did, Matt Paletti was Dan Goldman's student and came as a postdoc, and look, this is one of the many data sets, but now fitting the buoyancy frequency to the behavior as a function of depth, you see it's approximately logarithmic with scatter. And see, it varies by 2 orders of magnitude. So the characteristic oscillation period due to the buoyancy at the surface of the ocean or near the surface of the ocean might be 5 minutes, 10 minutes. But down deep in the ocean, we get to the ratio to the tidal frequency. Here at 1, we have the characteristic period would be 12 hours, 12.42 hours, the tidal frequency, period, tidal period. Whereas here it would be 10 minutes or 5 minutes. So now we decided to do experiments and compare in the laboratory with direct numerical simulations. And I'll skip that. Here's an experiment that was done with tidal flow given here by this arrow left and right. And this is a sphere, and you can see the waves generated, internal gravity wave generated here, 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 and here. And if you compare a simulation and experiment, this one's actually pretty old. You can see the agreement's reasonably good. It's gotten much better since then as we improved the measurements. Now, you look in the ocean, there's very nice topographic data that's become available only very recently with satellite measurements of NASA. And this is from JASON 1 and JASON 3. JASON 3 was just recently launched. And the improvement is going to be in the satellite data resolution for bottom topography, order of magnitude within another decade or so. So it's pretty remarkable. But you see, in the bottom of the ocean, you have a lot of ridges. You also see mountains here, 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 here. These are called seamounts. So you have ridges and mountains, and it's the tidal flow over these that produces the internal waves. And so how much power is produced? Well, you do linear function, Green's function analysis, as Nycander did a few years ago. And now these are knife edges, periodic knife edges, and they produce the waves traveling in the way shown there. And interestingly, they found that if the spacing was such, for the two heights divided by the separation L here was an odd integer, you get constructive interference of the wave produced here with the wave produced there, an infinite amount of energy. You get a divergence that appears in the calculation. Of course, there's no divergence, but there's a large amount of power. And so we did direct numerical simulations. This was done by Likun Zhang. And at that condition, same as had been done in the analysis, you get the power per peak was greater than you would get when you have an array than it would be if you had a single by some amount. What was surprising was it was not greater here if the angle of the waves was such that they came in interference with the neighbor here. And even if there was a peak here relative to other angles, other separations, but even this buoyancy frequency is small, so deep in the ocean, but you still have a virtual seafloor here and here. Now you go up from the bottom of the ocean to smaller depths in the ocean, and the waves come in because N is larger, the buoyancy frequency is larger. Waves come in at a smaller angle, and you have much more of the seafloor doesn't enter into the generation of these internal waves. Now, in the linear theory, as I mentioned, the power generated by bottom topography is proportional to the square of the height of the topography. And nobody's gone theoretically, paper and pencil, further than linear theory. So we did simulations with tall topography and found that a break at a certain topographic height, which is roughly 300 meters, depends on the normalization. There's a break in the slope, and you have the scaling is not h squared, but is linear. So all those estimates of the internal wave in the ocean based on the quadratic dependence are too high, because most of the power comes for the large heights up here. The large power comes, and the scaling is quadratic. And that's results from numerical simulations for random topography. Many topographies were synthesized, but that's not a rigorous result. That's a computer experiment, if you like, not a laboratory experiment. And then we presented that, and oceanographers said, oh, we were considering ridges, but the ocean has lots of mountains. And in fact, there are more than 33,000 mountains with a height of greater than 1,000 meters. Here is where they're located in the ocean. And if you go down to 500 meters, there's another additional 130,000 mountains that are that high. So a lot of mountains, they ought to have a big contribution to the energy in the oceans. So we did a lot of simulations together with a person who's at the University of Mississippi State University, Martin Bushman, and his graduate student. And this has appeared. And we have Gaussian mountains of different heights and spacings, and tidal flow from different directions and all of that, and calculate, given the mean spacing, the same as the mean spacing in the ocean and so forth. And we conclude the power from the mountains generated, the internal wave power, is not very much compared to that generated by ridges. And then we thought about it, and we said, of course not, because here comes the tide around up to a mountain, and it doesn't have to go over the ridge, lifting the dense water up over the ridge, changing that height of that dense water and producing internal wave. The water will just split and go around the mountain. So it's kind of obvious. After two and a half years work anyway. So now the focus of what we're doing is to say we want to calculate internal wave power from laboratory measurements. In the laboratory, you can't measure pressure fields. In the ocean, you can't measure pressure. You measure pressure at a point, but fields. You measure fields with a laser sheet and particle image velocimetry. Or you can measure by looking at the distortion, the refractive index of images passing through water. That's a stirring imaging. You can get the density perturbation field. So you get those fields. So we have a method developed particularly by a student of Phil Morrison. Phil Morrison is a theorist, plasma theorist, and his student Lee, to get from the velocity data alone the internal wave power, if you have velocity field. And now gone further, and from the density perturbation field alone, we have for constant n, we've already published that, but for any n, any buoyancy frequency profile, you can calculate from density perturbation data the radiated internal wave power. And that's in a draft manuscript. Well, anyway. So to try out direct measurements compared with simulations, we've done for a real density distribution. So this is just picking a set of data off of Iceland. And this is not density, but this is actually the buoyancy frequency. And you can see how it has one value, larger value near the surface, and as you go down, it has a smaller value as you go down towards the bottom. This is approximately a Tange profile. And we calculate in a simulation and conduct an experiment with this buoyancy frequency profile, and this is looking at the difference between the two. And the generation of the waves is here. They come down. There's a reflection here. You can see that going. You don't see much, because if the two match perfectly, this would be all white. Right? We're just as a shortcut to show that the whole method is working.
Are there uncertainty or heterogeneity?
Oh, this is, of course, not our data. This is ocean data, and they're the uncertainty in that particular measurement. Okay. So let me just conclude. So we looked at the way the wave power depends on the height of the topography, and it's proportional to h for all the small hills up to about 300 meters, but for taller hills, it's proportional to h squared. That's backwards. I just made this last night. This should be h squared, and this is h. That's after dinner last night. Okay. But we know which is which, right? And then there's this virtual seafloor, which reduces the amount from the existing efforts, estimates of the amount of internal wave power. So this realization reduces the amount from the rough estimate of Carl Wunsch of a terawatt. And this reduces it too, and this reduces the amount more, realizing this very large variation in the buoyancy frequency, which is high near the surface, but very small near the bottom, deep in the ocean. And you can forget about seamounts, they don't contribute. But the software we've developed in all of this that can be used to analyze experimental data or data from simulations is all on MATLAB Central, or some of it is yet to come, but it can be downloaded and used, because it's not that hard, but to generate the software would take time. Thank you very much.
Data that shows the buoyancy frequency as a function of depth. Is the King, you showed the King data slide.
Oh, yeah. I don't know what's the best way. Go ahead. What's the question about it?
Well, it just seemed like the buoyancy frequency at the very bottom, in most cases, was very close to, that one.
Oop.
That's nearby.
Oh, what happened? I had it. Shoot.
So it seemed like the buoyancy frequency at the very bottom was very close to the tidal frequency.
Oh, yes.
Is that coincidental?
Yes. So I didn't say anything about near the bottom. Yeah, you don't need what you say is true. That deep in the ocean, 5 kilometers, 6 kilometers, the buoyancy frequency drops to a value that's the same as the tidal frequency. So below that level, so that's a turning depth. Below that level, the internal waves are evanescent. They're exponentially damped.
So is that a coincidence that level's close to the bottom of the
That's a coincidence that it happens. It's a particular number. Why should it? Anyway, below that, but you do have tidal flow below that turning depth, and that tidal flow then produces, if that turning depth is not too far above the top of the mountain, you get tunneling through and waves produce, but they're weaker. It's just like quantum mechanical tunneling. Right? Yes?
Do you have any guess about what sense of scale for the transition between the two scaling regimes?
No.
300 meters?
No, I don't have a guess on that. And I also didn't give, so the rough estimate that's used in oceanography for the amount of power available to push the Gulf Stream or to in the oceans, internal wave power is about 1 terawatt. That's the number that's repeated over and over. We think it's more like half that because everything we look at reduces it. Yeah.
So, along the same line, you showed us what happens for random topography at the bottom. A lot of those seamounts occur in ridges that are part of linear island chains.
Yeah.
Is that
Okay.
something you could look at?
So, what's a seamount and what's a ridge, right? So we looked at that. You can have an axisymmetric Gaussian, or you can have the Gaussian with a cross section, which is a circle, or you can make it an ellipse. And how you can make the major, semi-major axis twice as big as the minor axis, or 3 times. By the time you get 3 times as long semi-major axis as the minor axis, it's already behaving like a ridge almost. So there's a transition there. So we looked at that.
So it would give you the upward.
Yes. So in that case, the bulk of the water goes up and over instead of around. Right. Exactly.
Okay, I'm afraid we have to move to another topic. Thanks, speaker again.